Hello and welcome to NPTEL MOOC on fiber optic communication systems and techniques. In this module, we are going to apply the systematic procedure to study slab waveguides. So, this will be kind of a review of the procedure that we have already been seeing because we applied it to parallel plate waveguide in the previous module. Now, most of the techniques or most of the steps that we have done is already for the analysis of slab waveguide, we have already accomplished that in the previous module itself. Okay. So, we have chosen the coordinate system which would be slightly revised for this problem, okay, to bring out couple of symmetry aspects of the problem. Otherwise, we are still going to choose rectangular coordinate system, Cartesian rectangular coordinate system, then express the transverse electric and magnetic fields in terms of the longitudinal electric and magnetic fields, write and solve the wave equation for the longitudinal component, apply boundary condition to obtain the characteristic equation and other constants of the solution, and finally, the step that you would be doing as an exercise would be to express all the other components, or rather from the expressions of the other components or the transverse components, you obtain the mode functions of them. Okay. So, we have already seen the first step of choosing the coordinate system, but I am going to change the coordinate system slightly, as I told you. Okay. We still have the interface or the waves propagating along the z axis, okay, but now my x axis will start at the center of the slab. Okay. Of course, since this is a slab waveguide, there will be a refractive index n1 here and a refractive index n2. We are going to assume perfect dielectric in the second medium as well as a perfect dielectric in the first medium, so that we do not really need to consider the losses. Okay. So, I have n1 here and I have n2 here, and now this plate will be, or this plane will be at x equals minus h by 2 and this would be x equals plus h by 2. Okay. Because see, we have seen that the center of symmetry would actually be at the center, as we saw in TE and TM case. So, what we called as odd function or an even function did not really have the same kind of a value of nu there. Okay. So, just to keep them redefine the symmetry properties, so I am going to change the coordinate system by moving up this way. Now, before we can even start the systematic procedure, I already know that if I am going to consider the transverse electric modes, then the only non-zero components that I am going to have will be Ey, Hz and Hx, of which Hz will have the following wave equation, which we have seen already: d square Hz by dx square equals minus k0 square n1 square minus beta square, okay, as long as your x is between minus h by 2 to h by 2. Okay. Now, this is the difference that you are going to get. So, in the previous parallel plate waveguide, we had only one equation which was valid inside the slab, okay, but outside Hz was assumed to be 0, far away from the interface, but now I can't do that. I have to assume d square Hz by dx square will be equal to minus k0 square n2 square minus beta square, because outside medium is all a perfect dielectric of refractive index n2. So, this is the case when x is greater than h by 2 as well as when x is less than minus h by 2. That is, it would be the same case over here for the lower part of it, or this is a so called substrate and this is the cover, and in between is the film, as we have seen. So, in the film you have this equation with n1, and in the substrate and the cover you have the equation here with n2, and we of course also know that n1 is greater than n2. This is from our simple ray picture where we were looking for total internal reflection as the cause of the modes being propagated. Okay. So, this is what the equations that I have. Of course, I also know how Ey is related to Hz. Okay. So, Ey is given by j omega mu naught divided by k0 square n1 square minus beta square del Hz by del x, okay, as long as you are within the film. So, let me write down this one. This is film, this is cover, and this is the substrate. So, inside the film you have k0 square n1 square. Outside of the film, whether we are talking about substrate or the cover, you have to replace k0 n square by k0 square n2 square. Okay. So, this is our equations that we have. Of course, I have not written down an expression for Hx. you can do that one as a part of the exercise of this problem. Okay. So, what sort of solutions should we consider? Now, we do know that if it was a perfect electric conducting walls, then there will not be any field outside. Whatever the continuity of the tangential magnetic field would be, that would have given rise to the surface currents, right. In this case, there is no possibility of a surface current, but still it may be possible for us to have a solution in this form. So, it is a sinusoidal solution, but the solution cannot go to 0 here at the boundary. Why? Because the continuity between two perfect dielectric is that the tangential components just be equal to each other. It does not say that the tangential component has to go to 0 here, only that these two will be equal to 0, and we do know that there are evanescent fields outside the film because of total internal reflection phenomena. So, these fields would actually decay in this exponential manner. So, the solution would look more or less like a sinusoidal field inside, but outside it would be an exponentially decaying field. These are the so called radiation modes or the decaying modes or the decaying fields actually, but inside it would look like a sinusoidal or cosinusoidal kind of a wave. And incidentally, this mode now will have what is called as TE0 mode. Okay. So, it will be a solution even when nu is equal to 0. The field is not going to 0 when you substitute nu equal to 0. Okay. The other higher order modes are equally possible. So, you might have the same kind of a decay constant or you might have a slightly different decay constant out there, but then the field itself could be something like this, okay, and then the field would be decaying around in that manner or maybe decaying in this case. Okay. So, outside it would still be decaying, but inside it would be a sinusoidal kind of a field. Same thing as in the parallel plate waveguide, this would correspond to nu equal to 0, this would correspond to nu equal to 1, but it is not so simple as I am writing it down. Okay. So, we are going to look at why it is not so simple, and the key to this kind of solutions lies in this expression. Okay. I am going to introduce couple of notations here. I will say kappa f square, which is the transverse wave number, to be defined as k0 square n1 square minus beta square, and I clearly want kappa f to be a positive quantity. Okay. So, only when kappa f is a positive quantity, I will have d square hz by dx square equals minus kappa f square times hz have a solution, okay, in the form of a cosine kappa f x plus b sine kappa f x. Okay. So, this should be the condition within the film. Now, outside the film I am going to define a quantity gamma. Now, this should remind you of the decay constant, which is what I was hoping that you would be reminded of, and this gamma square will be defined as beta square minus k0 square n2 square, right. So, we have already seen earlier that the allowed values of the longitudinal component would lie between k0 n2 to k0 n1. So, beta can lie somewhere over here. We have seen this already in the previous module. So, now once I have defined this gamma, okay, as beta square minus k0 square n2 square, clearly gamma is positive, kappa f is also positive, but the solutions are going to be different, okay, because the solution here will be d square hz by dx square will be equal to. So, this is in the outside the film that I am considering. So, outside the film this fellow will be positive now, okay, and what you will have is gamma square. The solution here was gamma square being positive and kappa square being positive. Okay. So, this would be gamma square h z for x greater than h by 2 and for x less than h by 2. Now, here is an interesting thing. Okay. The solution inside is fairly okay, but the solution for x greater than h by 2 must come by assuming gamma to be a positive quantity. Oh, so did we get this wrong here? Hold on a minute. So, I had minus k0 square n2 square minus beta square. So, I defined gamma as so gamma is beta square minus k0 square n2 square. The solution is in this form. So, when beta is greater than k0 n2, then I am going to get two solutions for this one, right. So, gamma will actually be equal to square root of beta square minus k0 square n2 square plus or minus, correct, and I can't choose the plus sign for the field outside or in the cover, right. So, when I am looking at x greater than h by 2, I cannot assume gamma square to be a positive quantity. In fact, gamma square is just defined in this way, but gamma can be plus or minus, and I have to choose the minus quantity over there. Okay. So, when I choose a minus quantity, the solution for h z of x will be, let us say, c e power minus gamma x minus h by 2. The reason why I have written x minus h by 2 is to simplify the boundary condition. So, at x equal to h by 2, this exponential term will be equal to 1, and therefore, the value of h z as you come in from the cover will be equal to just c. Okay. But when x is less than h by 2, the field that I need to consider will have a positive gamma value. Why? Because there x will be negative. Okay. So, I will have d e to the power plus gamma x plus h by 2. Okay. So, again x is negative. So, please remember that x is negative and x is greater than minus h by 2. So, because of that, the term in this bracket in the exponential function will be negative, and it would of course be corresponding to a decaying field. Okay. So, unlike the previous case where we had fields which were 0 completely outside the waveguide, now the fields are non-zero outside the waveguide. So, we have 3 solutions now, one corresponding to the field in the film, the solution corresponding to the field in the cover, and the solution corresponding to the field in the substrate. As I told you, I have assumed that this waveguide that I am considering, the slab waveguide, is a symmetric waveguide. Therefore, cover and substrate both have the same refractive index. Now, our step would be to find out the relationship between kappa f, gamma, beta. I mean, our goal is to find out what is beta, and I cannot get that one unless I know how to obtain kappa f and gamma. So, somehow I have to get a relationship between these, and that relationship will be obtained provided I know the characteristic equation for beta, and to do that one or to derive that one, I need to apply the boundary conditions. Okay. So, I am going to apply boundary conditions, and what are the boundary conditions? Well, we had h z, which is a tangential component. This should be continuous at the two interfaces, x equals plus or minus h by 2, and there is a second condition that I need to obtain, that would be in the form of E y, right. So, I need to have E y of x also being continuous at x equals plus or minus h by 2. Okay. So, what would be E y of x now? E y of x outside would be equation which would be decaying, and then within the film it would be sinusoidal. So, I know that E y is related to d h z by dx, that is, it is related to the derivative of that. So, if I write down E y of x, that would be j omega mu naught divided by k 0 square n 1 square minus beta square, when I am writing this equation inside the film, and then you have d h z by dx. Okay. So, d h z by dx and k 0 square n 1 square minus beta square is nothing but kappa square, and then d h z by dx inside the film will pull kappa f out and then convert cosine to sine and sine to cosine, just like the previous case. So, I will have a kappa f outside, and then I have minus a sine kappa f x plus b cosine kappa f x. Okay. I have two kinds of solution, one is a sine solution, one is a cosine solution. What I am going to do is that I know that this field that I am considering is actually an even kind of a function, right. So, I have this as an x axis. So, I have this as x equal to minus h by 2, and this is x equal to plus h by 2. If I were to assume this is solution of the sine form, so this would be the sinusoidal function like this within the film. So, this would correspond to the odd modes. If my solutions are assumed to be of the form of cosine, then they would actually be something like this, which would be the even modes. Okay. So, I am going to consider only even modes in this problem. So, I will retain b and I will set a equal to 0 by myself. Okay. I mean, I can consider separately the solutions. So, I am going to first solve the problem with b and then leave the problem with a as an exercise for you. Okay. So, I have kind of simplified my problem just to obtain an equation or just to understand the even terms. We will look at what happens for the odd terms also later on. Okay. Until then you will be actually solving them as an exercise. Okay. So, E y of x is given by j omega mu naught by kappa f. There is a constant b here, then I have cosine kappa f times x. This is for the field inside the film, right. The corresponding Hz of x will be of the form. So, let us look at Hz of x. Hz of x, because we have set a equal to 0, will not have this term. So, it will have only this b sin kappa f x term. So, this would be b sin kappa f x. Okay. This is in the film. What would happen in the cover region? So, in the cover region, Ey of x will be equal to j omega mu naught divided by k0 square n2 square minus beta square, and then derivative of Hz with respect to x. And in the cover, we already know that Hz goes as some c, but when you go to the field in the cover, you will have, and then you differentiate this one, you are going to pull this minus gamma out, correct. So, you are going to pull this minus gamma out, which means that this would be minus gamma e to the power with a constant c minus gamma x minus h by 2. Okay. And k0 square n2 square minus beta square is basically minus gamma square. So, there is a minus and a minus sign on both sides. So, I can remove this one, and then instead of writing this k0 square n2 square, I can just write this as gamma. Okay. So, this is when x is greater than h by 2, and similarly when x is less than h by 2, I know that the solution is in terms of d, and when you differentiate this one with respect to x, gamma will be pulled out, and I know that there is a minus somewhere out there. So, I will have a minus j omega mu naught by gamma, and the constant will be d e to the power plus gamma x plus h by 2 when x is less than minus h by 2. So, for the fields in the substrate, this is the equation. Okay. Now, apply the boundary condition 1, that is h, or rather let us write down the boundary condition first in terms of Ey. So, I have Ey at x equal to plus h by 2 being continuous, that is, if I come from this exponential function, then the solution here should be kind of continuing naturally into the film region, which means that the value of the field in the film must exactly match the value of the field outside at the boundary, right. So, you have two fields or two different solutions, and these two solutions must match or match up at this particular boundary, and that is what should happen. I mean, that is what is the boundary condition. So, you come from the top and you are within the film, these two values should be equal to each other. Now, you go back to the expressions that we have written, and in the expressions that we have written, if you come from the field direction at x equal to h by 2, so you will have this cosine kappa f h by 2, this j omega mu naught by kappa f will all be remaining in the same way, and then you will have Ey of x coming in from the whatever that evanescent side will be c e power minus gamma at x equal to h by 2, this exponential function will be unity. So, the equations that I actually get from the evanescent side will be j omega mu naught, let me go back and write down this one. So, j omega mu naught divided by gamma times c, that must be equal to j omega mu naught by kappa f. So, I have j omega mu naught by kappa f, okay, times b cosine kappa f h by 2. Okay. So, this is the equation that I am going to get from the from applying the boundary condition at x equal to plus h by 2 on Ey component. Of course, I do have a component Hz which is tangential component for the magnetic field, because there are no surface current layers that we have assumed. This component would also be continuous, and coming in from the evanescent side or the cover side, Hz at x equal to h by 2 will have b sin kappa f, this will be coming in from the film side, but if you are coming in from the Hz case, that would be c itself, okay, Hz at x equal to h by 2, that would be c, which will be equal to, on the right hand side it would be equal to b sin kappa f h by 2. So, I will have b sin kappa f h by 2. So, I have these two equations. Luckily, c is there in the left hand side, b is there on the right hand side. If I divide this equation by this second equation out there, what do I get? So, I will get sin kappa f h by 2 divided by cosine kappa f h by 2, okay. That should be equal to, so sin, and there is also j omega So, j omega mu naught is constant on both sides. So, I can actually remove them here itself. So, I will have 1 and 1 here. So, I will have b sin kappa f h by 2 divided by b cos kappa f h by 2 divided by kappa f. So, kappa f goes on top. This must be equal to c divided by c by gamma. So, gamma goes on top, b cancels out from these equations, sin by cos is essentially tangential tan function. So, you have tan kappa f h by 2 being equal to gamma by kappa f. Now, is not this the same equation that we obtained from transverse resonance condition, which would relate kappa f, the transverse wave number, to the decaying constant gamma? This is exactly the same equation, and if you were to, instead of assuming that electric field would be in the form of a cosine kappa f x, if you had assumed it would be in the form of sin kappa f x, you would have obtained the equation that would have corresponded to the odd modes, right. There you would have, instead of tan, you would have cot, and then instead of gamma by kappa f, you probably would have kappa f by gamma with a minus sign, right. So, something very similar to what you have seen from the ray picture, you have the same equation. Now, it is not only for the characteristic equation that we went through this step, it is because in addition to obtain the characteristic equation, I also know how the field components E y, H x and H z themselves vary. So, why is that important? Because if I were to change the constituent parameters of the slab waveguide, for example, I make n1 greater than n2, already I know that, but if I were to increase the index contrast by a larger value, what would happen? If you were to increase the contrast by a larger value while keeping the same slab waveguide thickness, then the field gets more and more confined inside the film itself. Okay. So, you have the field otherwise. So, what happens when n1 and n2 are not very different, still maintaining n1 greater than n2, then some of the field actually starts to decay outside or leak outside the film. So, if you want a better confinement, you want to make n1 greater than n2 while keeping the same thickness, assuming, right. Of course, if you play around with thickness as well as with the index contrast, then you can essentially get whatever profiles you want, but the important point is that you would not have gotten this insight, okay, unless you would have known how the field components actually look like when they are propagating inside the slab waveguide. So, and that is where the systematic procedure is so useful. Okay. Of course, as a mathematical exercise, this is all fine. The physical intuition is still what we talked about in the ray theory approach, but now mathematics or Maxwell's equations helps us to complete that incomplete physical intuitive picture. Okay. So, physical intuition picture is very good, it gives us basic characteristics, but it will not tell us how the field quantities themselves will look like, and that is precisely what this analysis has given you. Okay. Now, although we have written down the equation, the characteristic equation tan kappa f h by 2 equals gamma by kappa f, please remember that solving this type of an equation is very difficult. In fact, it is not possible analytically, because kappa f contains beta, which is unknown, gamma contains beta, which is also unknown, okay. And then you have a tangential function of x being equal to some kind of a tangential function out there, which makes your life difficult, because this is called as a transcendental equation, and these equations are to be solved either by graphical methods or by numerical methods. We have considered only transverse electric modes, we have not considered transverse magnetic modes, but the procedure would be essentially same. There you would in fact start with you would in fact start with Ez and then express Hy and Ex in terms of Ez. Hz will be 0 in that particular mode for those type of polarized modes. So, the procedure would essentially be the same, and you would arrive at a characteristic equation, which again you have to solve either numerically or graphically. Okay. One final point before we close this discussion on slab waveguides. Of course, we will have one more module discussing the properties, but for today we wrote all those constants, right, A, B, C and D, but we never found out what those constants were. In fact, to find out those constants, you have to apply the boundary condition on the substrate and the film layer as well, plus you have to impose the total power constraint, okay, which means that if I am sending in certain amount of power into a particular mode, then that power will essentially determine one of those constants. So, it is possible for you to apply boundary conditions at the two layers, eliminate two constants, arbitrary constants from them, and you will be left with only one arbitrary constant, which you will be fixing with the help of total power condition. Okay. Since that is little complicated, I mean the mathematical steps are tedious, the procedure is not complicated. So, I have decided to skip that step and instead give that as an exercise to you when we come to when we come to the assignments in this course. Okay. So, in the next module we will revisit these equations and then see how to solve them graphically and also study couple of properties of these modes, and then we will be talking about single mode fiber. Okay. Until then, thank you very much.